Hello, everyone. Welcome to this edition of the webinars by AAC Kalkitech. I'm Shweta Bhatt from the marketing team here to your host today. Today's webinar is on AMI 2.0, the future of smart metering infrastructure. And we'll be covering major points of how AMI 2.0 is making a significant change in the industry. Before we begin, here are some hygiene points. Please note that this is a listen-only webinar and make sure your microphone is muted and the video is turned off. If you have any questions, please feel free to use the chat box. We will compile the questions at the end of the session and get back to you. Try to answer it in the session itself, or else we will email you the answers. Our speaker today is Aparna Raghunath, Business Development Manager at Metering Services, Kalkitech. She has been with the organization for 6 years now, and her chief interests are design and implementation of DLMS protocol solutions, consulting and training in protocols like DLMS, COSAM, etc. Yeah, so I will now hand over the session to Aparna.
Thank you, Shweta. Hi, all. So now we'll get started with our topic for today, AMI 2.0, the future of smart metering infrastructure. In this session, we will be discussing what is advanced metering infrastructure or AMI, the evolution of meters from AMI 1.0 to AMI 2.0, and also the key features of AMI 2.0. Let's now dive into our session. Firstly, let's have an introduction to AMI, or what do we mean by the term advanced metering infrastructure. Advanced metering infrastructure is an integrated fixed network system that enables two-way or bidirectional communication between utilities and consumers. AMI comprises of smart meters, communication networks, and data management systems that helps to enable two-way communication. The system will collect, store, analyze, and present energy usage data, which will help the utility companies to monitor electricity, gas, and water usage in real time. So we now know what an AMI is. But how is this different from the earlier systems utilities used? Let's now take a quick look at the key differences between AMR, automated meter reading, and AMI, advanced metering infrastructure. AMR was the predecessor to AMI, so these differentiators will help us understand what makes AMI the key enabler of smart grid. First is the communication aspect. AMR systems support only one-way communication, which means the meter sends data, but it can't receive commands. In contrast, AMI enables two-way communication, allowing both data transmission and control commands. Second is how the data is fetched. With AMR, meter data is collected periodically or manually, often using handheld units. But AMI enables scheduled or on-demand reads, making the process more efficient and responsive. Third is the remote control aspect. AMR lacks this capability. However, AMI allows remote connect or disconnect as well as firmware upgrades, which significantly improves the operational efficiency. Next, we have data analytics. AMR provides only limited data, whereas AMI, on the other hand, offers real time insights which are crucial for load management, outage detection, and improving grid reliability. Finally, on consumer interaction, AMR system offers minimal engagement. But with AMI, consumers can interact via portals or mobile apps, gaining visibility into their usage and helping promote energy efficiency. So, these key differentiating factors that we have discussed highlight how AMI provides a smarter, responsive, and consumer engaged infrastructure than AMR. Now that we understood what AMI is at a high level, let's take a closer look at how it was first implemented, referred to as AMI 1.0. Now, this version marked the beginning of digital metering infrastructure using centralized systems and batch based data collection. Let's see how the architecture looked and what its key characteristics were. AMI 1.0, as mentioned, represents the first generation of advanced metering infrastructure where the architecture is largely centralized. Smart meters communicate with the head-end system or monitoring station using basic communication technologies such as RF, PLC, or GPRS. And the head-end system handles all meter provisioning, data collection, and even management. Having discussed the architecture of AMI 1.0, let's now head to the key characteristics and limitations of AMI 1.0. AMI 1.0 introduced several foundational capabilities to utilities. Key functions include automated meter reading, reducing the need for manual reads, basic outage detection, remote disconnection and reconnection for service control, and seamless integration with billing systems. However, the architecture had notable limitations. First, the meters had minimal edge intelligence. They mostly acted as passive data loggers, not capable of local decision making or processing. Second, data was collected in scheduled batches, leading to high latency and limited real time visibility. Finally, the system was tightly coupled. Hardware and software often came from the same vendor, resulting in poor interoperability and difficulty integrating diverse technologies. And these limitations eventually drove the need for a more flexible, responsive, and modular metering infrastructure. Let's now in detail discuss the key industry drivers for change which led to the transformation in energy and utilities sector. The first industry driver is the decentralization of the grid. Traditional centralized power systems are evolving into decentralized networks with distributed energy resources or DERs like solar panels, wind turbines, and energy storage systems. And this shift demands new approaches to grid management and coordination. The next driving factor is the need for real time decision making. With dynamic loads, variable renewable energy, and evolving customer behavior, utilities need systems that enable quick, data informed decisions to maintain reliability and efficiency. Third is data driven operations. The industry is increasingly relying on data analytics to optimize asset performance, forecast demand, and improve the operational efficiency. And this requires robust data collection, processing, and interpretation capabilities. Fourth, and one of the most important driver is cybersecurity threats. As infrastructure becomes more digitized and interconnected, it also becomes more vulnerable to cyber attacks. So, protecting critical energy systems from cyber threats is now a top priority or concern. Fifth is the customer expectations. Modern consumers expect reliable service, transparent billing, and more control over energy usage, along with sustainable options. Hence, utilities must adapt to meet these evolving expectations of the consumer. Lastly comes policy and regulation. Governments and regulatory bodies are pushing for cleaner energy, smarter grids, and more customer centric operations. And compliance with these evolving regulations is thus a significant driver of change. Now that we've seen the key industry drivers pushing the utilities to evolve, the next question becomes, how do we respond? One major enabler of this transformation is the shift to next generation advanced metering infrastructure, or AMI 2.0. And here we are going to discuss the core benefits of adopting AMI 2.0, which is the next evolution of smart metering and grid intelligence. The first benefit is the real time responsiveness. AMI 2.0 supports instant data communication, enabling faster detection of outages, anomalies, and consumption changes. Second is the scalability and flexibility. AMI 2.0 is designed to handle future growth with more meters, more devices, more complexity, while adapting to changing utility needs. Next is the advanced cybersecurity. With increasing cyber threats, AMI 2.0 embeds stronger encryption, authentication, and security monitoring mechanisms. Fourth is the support for DERs and EVs, distributed energy resources like solar panels and electric vehicles can be integrated and managed efficiently, enabling a two-way power flow in AMI 2.0. Next, we have enhanced consumer engagement. Consumers gain more access to usage data, dynamic pricing, and control options, leading to better awareness and participation in energy saving. Sixth is the compliance and innovation readiness. AMI 2.0 ensures readiness for evolving regulatory demands and opens doors to innovative use cases like demand response, peer to peer energy trading, and grid automation. Let's now in detail discuss about AMI 2.0, which is the foundational pillar for digital utility of the future, which enables resilience, intelligence, and customer centricity. Let's start with a quick introduction to AMI 2.0. AMI 2.0 represents the next generation of advanced metering infrastructure, which is far beyond just reading meters. It's a modern, distributed, and interoperable metering ecosystem that brings together multiple vendors and technologies seamlessly. Unlike traditional systems that focus solely on meter reading, AMI 2.0 emphasizes grid intelligence and automation, enabling the grid to think and act. It supports real time decision making, leverages edge computing for local analytics, and is built to handle bidirectional energy flow, which is critical with the rise of solar batteries and EVs. So essentially, it transforms the grid being reactive to being proactive and intelligent. Moving on to a comparison now between AMI 1.0 and AMI 2.0, which showcases why AMI 2.0 is the future of smart metering and why a transition from AMI 1.0 is critical. First, let's start with architecture. AMI 1.0 is centralized, meaning all the control and intelligence are located at a central server, whereas AMI 2.0 is distributed and cloud or edge enabled, allowing decisions and processing to happen closer to the devices. Next is communication. AMI 1.0 typically used delayed one or two-way communication, but AMI 2.0 enables low latency real-time communication, which is critical for fast decision making and control. When it comes to intelligence, AMI 1.0 relies heavily on the central system. Whereas in AMI 2.0, the intelligence is pushed to the edge, to meters and field devices, empowering them to make local decisions and reduce the burden on the central system. In exceptional cases, it could be centralized as well. Coming to data handling, AMI 1.0 uses batch processing, which introduces delays. On the other hand, AMI 2.0 supports event-driven and streaming data, allowing for faster reactions and continuous data flow. Lastly, on cybersecurity, AMI 1.0 often treated cybersecurity as an addition. In contrast, AMI 2.0 has built-in multi-layered cybersecurity to meet the complex challenges of modern grids, making it more dynamic, intelligent, and secure. Coming to the key features of AMI 2.0, as discussed, one of the first important feature of AMI 2.0 is the edge intelligence, which enables smart decisions to be made directly at the meter or field device, improving responsiveness and reducing the dependency on central systems. Next, we have interoperability, ensuring devices and systems from different vendors can seamlessly communicate, which is essential for scaling and integrating with diverse utility ecosystems. Third is real-time communication and event streaming. AMI 2.0 can instantly detect and react to changes, whether it's a fault, outage, or abnormal usage, enabling proactive operations. Fourth is the cloud native architecture. The system is built to fully utilize cloud environments, offering better scalability, flexibility, and integration with other digital services. Next is the advanced cybersecurity built in from the ground up, providing multi-layered communication against evolving threats, not just at the central system, but all the way down to the device level. The system is also consumer centric, meaning it is designed to empower consumers with insights into their energy usage and enable more control through features like demand response. Finally, AMI 2.0 is self-healing and resilient. It can automatically detect faults, reroute data, and recover from failures with minimal human intervention, ensuring higher system availability and reliability. Moving on to the architecture overview of AMI 2.0. At the center is the smart meter, which connects to two major systems. On the right, we have the universal metering head-end system, which communicates using the DLMS protocol to handle meter to cash functions like billing, MDMS, and smart meter operating center. On the left, the meter also connects to a distributed intelligence hub using protocols like Modbus, DNP3, or IEEE 2030.5. This hub supports applications like DERMS, SCADA, and DMS, enabling real-time grid automation and distributed energy integration. Coming to the bottom, you can see the meter also interacts with distributed generation through solar panel system connected to a smart inverter and also the EV charging system, making the AMI 2.0 ready for future smart grid needs. So this shows how AMI 2.0 supports both operational and commercial use cases in a distributed and intelligent way. Next, let's discuss the key benefits of AMI 2.0 from the utility angle. AMI 2.0 improves operational efficiency by enabling automation, reducing manual interventions, and speeding up service processes. It also enhances grid reliability by providing real time data and quicker fault detection, making the grid more stable and responsive. The architecture is designed for scalability and flexibility, allowing utilities to expand as needed and integrate new technologies with ease. AMI 2.0 also supports regulatory readiness, ensuring utilities can comply with evolving standards and requirements. Finally, it enables cost optimization by reducing operational costs, energy losses, and improving asset utilization for the utilities, which help utilities deliver better, smarter energy services. Now, coming to the key benefits offered by AMI 2.0 for the users or consumers. Firstly, AMI 2.0 provides real-time usage insights. So users can monitor their energy consumption instantly and adjust usage to save money. It ensures billing transparency and accuracy, reducing the disputes by providing clear, timely billing data. Next, users experience greater empowerment and engagement through better visibility and control over their energy choices. And lastly, it enables faster service, whether it's new connections, disconnections, or issue resolution with its automation and remote access features, enhancing the customer experience significantly. Heading to the various use cases of AMI 2.0, showing how it adds value across various domains in a smart grid ecosystem. The first use case is for advanced demand response. This allows utilities to control customer loads in real time, helping to reduce peak demand and prevent grid overloads during high consumption periods. Second is the DER integration, enabling seamless inclusion of distributed energy resources like rooftop solar batteries and electric vehicles into the grid, allowing more sustainable and decentralized power management. Next is the grid analytics. It helps in identifying the faults early and optimizing voltage at the grid edge, ensuring grid stability and efficiency of electricity delivery. Fourth is the dynamic billing. This allows real time pricing based on actual energy usage and grid status, encouraging more responsible consumption and supporting utility revenue models. Next is for electric vehicle charging. AMI 2.0 supports smart charging capabilities and vehicle to grid services which help balance the grid load and promote EV adoption. Sixth is outage restoration benefits from AMI 2.0 by enabling quicker fault detection and resolution through improved network visibility, which reduces the downtime for consumers. And lastly, consumer apps provide users with access to real time energy usage data through mobile and web platforms, empowering them to monitor, manage, and optimize their consumption effectively. So by now we have discussed what is AMI 2.0, its key benefits and use cases. Next, let's discuss the main challenges that we need to overcome to deploy AMI 2.0 solutions. First is the high initial investment. The significant upfront cost involved in infrastructure upgrades, smart meters, communication systems, and software platforms could be a challenge for utilities, especially in developing markets. Second is the integration complexity. AMI 2.0 often needs to interface with existing legacy systems and multiple vendor technologies, and ensuring seamless interoperability between meters, hidden systems, and utility backend platforms further adds to the deployment complexity. Third is the cyber security risks, as AMI 2.0 involves millions of endpoints and real time data transfer. It opens up new vulnerabilities. Protecting customer data and grid operations becomes a top priority. Fourth is the regulatory hurdles. Compliance with evolving regulations around data privacy, grid standards, and utility operations can slow down the deployment. Regulatory uncertainty or misalignments between stakeholders can also further delay rollout and increase the costs. Last comes data overload. With a huge volume of real time data generated by smart meters and edge devices, utilities often struggle with effective data management. So, addressing these challenges are critical for our migration to AMI 2.0. Once we address these challenges, we have to think about a suitable strategy for migrating from AMI 1.0 to AMI 2.0. So, we'll now discuss the migration strategy that we need to follow while we are migrating from AMI 1.0 to AMI 2.0. The first step is the assessment and planning phase. This is the foundational step where utilities evaluate their existing AMI 1.0 infrastructure. The goal here is to identify the current gaps, define target outcomes with AMI 2.0, and prepare a roadmap. This involves technical audit, business case analysis, and engaging all stakeholders early to ensure alignment. Second is the hybrid coexistence model. Since a full replacement of AMI 1.0 systems isn't always feasible in one go, a hybrid model is introduced. And this allows both AMI 1.0 and 2.0 systems to run in parallel. This stage ensures the continuity of operations while gradually integrating AMI 2.0 features, minimizing the risks and disruptions. Then we have the next stage, which is protocol interoperability, which is a critical step in ensuring that devices and systems from both generations can communicate seamlessly. This includes adopting protocol converters, upgrading hidden system, and ensuring that data from AMI 1.0 meters can still flow into the upgraded hidden system platforms without any loss or errors. Fourth is the phased rollouts stage. Migration is carried out in a staged manner, either region wise or customer segment wise. This minimizes the impact of any issues and helps utilities fine tune their approach as the rollout progresses. The lessons learned from early phases are also used to optimize the subsequent ones. Finally, last, we have the validation phase. This final step ensures that the integrated validation is happening correctly and AMI 2.0 system is functioning as expected. Validation includes field testing, performance monitoring, and verifying interoperability and data accuracy. So, to summarize, this migration strategy offers a structured and low risk pathway to modernize the utilities metering infrastructure, enabling future ready capabilities like enhanced data analytics, better customer engagement, and integration with DERs and smart grids. Now that we've seen the step-by-step strategy for migrating from AMI 1.0 to AMI 2.0, it's important to understand what enables this transition to be effective and future ready. Let's now discuss the role of standards and interoperability in AMI 2.0. Firstly, using open standards enable flexibility, which allows utilities to integrate products and solutions from multiple vendors. This flexibility helps avoid vendor lock-in and ensures a more competitive and innovative ecosystem. Second is the interoperability. When systems are interoperable, it's easier to switch vendors, upgrade components, or scale operations without being tied to proprietary solutions. And this empowers utilities with more control and cost efficiency. Next, we have faster integrations, standards based systems communicate more easily, which means new devices, applications, or platforms can be integrated faster, whether it's adding new meters or demand response systems. Fourth is future proofing investments. By aligning with standards, utilities ensure that their infrastructure remains relevant as technology evolves. It minimizes the risk of systems becoming outdated and it protects long term capital investments. Lastly, we have regulatory alignment. Many national and international regulatory bodies now mandate or recommend adherence to open standards. And following these ensures compliance and readiness for future regulatory shifts. We have just seen how standards and interoperability are critical in AMI 2.0. They help ensure flexibility, reduce vendor lock in, and enable faster, future proof integrations that align with regulatory needs. Now, let's look at how this plays out, specifically for DLMS, which is the backbone of smart metering. I'll now walk you through some of the key DLMS enhancements that will help us meet AMI 2.0 requirements. The first enhancement is for dynamic pricing and related services. We will need to extend tariff and register objects to support flexible models and personalized programs. Second is DER integration. We have to add DLMS objects to monitor distributed resources, handle related alarms, and provide remote control capabilities. Coming to the third enhancement on EV grid planning, here we'll need to enhance the model to capture EV specific data, detect unregistered charging, and enable load shifting. And finally, for revenue protection, tamper detection objects have to be added and strengthened with automatic tamper reporting enabled and secure firmware updates to maintain the integrity. So these discussed enhancements will ensure that AMI 2.0 objectives are met while keeping our DLMS systems future ready. Now comes the next question. How can you implement this and bring AMI 2.0 to the real world? That brings us to the next part, how we at Kalkitech have been engaging to enable this shift toward AMI 2.0. Our journey toward AMI 2.0 is mainly centered on three core engineering pillars: platform foundations, protocols, and edge intelligence. Now, these aren't just technical checkboxes, they reflect the breadth of real world implementations we have been a part of. We'll discuss each of this pillar in detail. First is the platform side. We have been working extensively with lightweight containerized environments that can support the growing demands of AMI 2.0 meters. These platforms often need to run securely and efficiently under tight memory constraints. We have deployed on ecosystems like AWS Greengrass Lite and hypervisors, bringing the cloud native thinking into embedded contexts. Our involvement with standardization groups like the DLMS UA Edge Gateway Initiative, the E4S Alliance, and GEISA has also helped us to actively shape the reference architectures that utilities and vendors can further build upon. The second pillar is protocols. Now, interoperability isn't possible without robust protocol implementations. And that's where a major part of our engineering effort has been focused. We maintain and evolve production grade DLMS stacks, which have powered millions of live meters today across the globe. Also, when manufacturers have specific needs, we have developed custom protocol stacks from the ground up, including support for MQTT, lightweight machine to machine protocol, and other emerging technologies. So, if you are getting started with developing an AMI 2.0 compliant meter or hidden system, these DLMS stacks provides you a base stack on which you can customize according to your requirements. Both the stacks, both the server and client stacks, supports the addition of all the DLMS enhancements that are required for AMI 2.0 compliance, which we have discussed in our previous slide. Also, importantly, we have also built test tools and simulators that are used for protocol validation and hidden system scalability testing. We have also embedded protocol stacks into reference meters to support certification workflows. Moving on to the edge intelligence side, once the platform and protocols are in place, the next leap is to bring intelligence to the edge. letting the meter or gateway make sense of the data before sending it upstream. And here we have engineered embedded modules for use cases like non-intrusive load monitoring, NILM, power quality event detection, solar disaggregation, and hosting capacity estimation. And these applications go beyond simple data capture. They transform the meter into an active node in the grid, offering actionable insights right at the edge. So, through these three pillars, foundational platforms, interoperable protocol stacks, and intelligent edge applications, we have been contributing to the ecosystem's evolution towards AMI 2.0. And more importantly, we are grounding our work in the values of interoperability and future readiness that the AMI 2.0 demands. For further information on our role and engagement in shaping AMI 2.0 solutions and to get a detailed overview of our solutions, feel free to contact us for a detailed discussion. The contact details will be provided at the end of the session. Moving on, let's now discuss the future trends in AMI and smart grid evolution. The first future trend that we are seeing is a rise of AI driven grid intelligence. Utilities are increasingly leveraging AI and ML models to forecast demand, detect anomalies, and optimize operations. Smart meters serve as real time data sources feeding these models, enabling more responsive grids. Secondly, there's a big push toward edge computing at scale instead of sending all data to central systems. Edge devices, meters, and gateways are being equipped to process and analyze data locally. This helps reduce the latency and bandwidth needs and supports faster decision making, especially on the grid disturbances. The third trend is the growing role of prosumers and the rise of transactive energy. Consumers are now also producers, whether through rooftop solar or storage and AMI systems has to be retooled to support real-time pricing, bidirectional energy flows and energy trading models. Fourth, to support these evolving use cases, AMI networks are evolving to include 5G and other advanced connectivity options, and this is enabling high speed, low latency communication even in dense urban and remote rural settings. Fifth, we are witnessing grid decentralization with distributed energy resources and microgrids on the rise. AMI systems must operate in a decentralized yet coordinated manner, often across multiple stakeholders and regions. And finally, integrated utility platforms are becoming essential. Utilities are moving toward unified platforms that bring together metadata, grid intelligence, DER management, billing, and customer engagement with AMI acting as the common thread that ties them all together. In short, AMI is no longer just an endpoint data collector, it's evolving into an intelligent, real time distributed infrastructure layer, enabling the smart, responsive, and resilient grids for the future. And with this, we are concluding our webinar for today. Let's wrap up by revisiting some key ideas that summarized the journey towards AMI 2.0. To begin with, AMI 1.0 laid the groundwork. It brought in digital metering, remote data collection, and billing automation. But over time, its limitations in scalability, speed, and adaptability became clear, especially as the grid demands evolved over time. And this is where AMI 2.0 steps in. It represents a shift from centralized control to real time decentralized intelligence. It's built on platforms that support distributed processing, cloud native infrastructure, and data driven grid operations. However, this transition only works if we get standards and interoperability. Open protocols ensure that we don't get locked into specific vendors or technologies. They enable future proof systems that can grow, evolve, and interconnect seamlessly. But the shift to AMI 2.0 can't happen all at once. And hence, migration needs to be phased and strategic. It should minimize disruptions while maintaining compatibility with existing systems. And lastly, looking ahead, it's clear that future trends like AI driven analytics, edge computing, and the rise of prosumers will shape the grid. AMI is not just enabling these trends, rather, it's becoming a core part of them. So, whether you are designing, implementing, or evolving AMI systems, these are the building blocks to keep in your mind as we collectively move towards a smarter, more responsive grid for the future. Thank you so much for attending our webinar today. We hope the session has helped you to understand how AMI 2.0 is going to shape the future of smart metering infrastructure. Let's now discuss your questions moving on to the Q&A session.
Yeah, thank you, Aparna, for that informative session. Here are some questions the audience has asked. How do utilities handle firmware updates in AMI 2.0 environments?
The firmware is updated remotely in batches using secure scheduled transfers via the hidden system or concentrators. This can be done. The process is similar to that of in AMI 1.0.
Okay. Another question is how often should meters send data in an AMI 2.0 setup?
Typically, we are expecting every 15 to 60 minutes, like how we have in AMI 1.0, but it's configurable based on utility needs and communication constraints. You can configure it according to your requirement.
Okay. Can AMI 2.0 help with outage management?
Yes, meters can send last gasp outage
Aparna, are you there?
alerts. Yes, Shweta, can you hear me?
Yes, yes, yes.
Yes. So what I was telling is that
Okay, we have
yes,
another question.
AMI 2.0 can help with outage management. Meters can send last gasp outage alerts or power outage alerts to aid fault localization and faster recovery. Yes, Shweta, we can move to the next question.
Yeah, there's another question that can AMI 2.0?
Shweta, could you please repeat the question?
Yeah, can AMI 2.0 support multiple communication technologies at once?
Yes, it does. It supports hybrid networks using RF, PLC, cellular, or Ethernet. Within the same deployment itself, you can use multiple technologies.
Yeah, uh, did you get that?
Shweta, your voice is breaking. Can you please repeat the question?
Yeah, sorry. Is there a way to simulate AMI at large scale before deployment?
Yes, there is. Simulators can be used to model large scale behavior. In fact, we can use Kalkitech's DLMS million meter simulator, which will help you to simulate an environment with millions of meters, which can be used to validate the performance of your developed hidden system when it's communicating with millions of meters. So, all the actual scenarios that the hidden system could be exposed to can be tested prior to the deployment. So, yes, a large scale AMI can be virtually simulated using Kalkitech's DLMS million meter simulator.
Okay. Um, we have another question that says, uh, can AI 2.0 systems handle multiple tariff configurations?
Okay,
So,
so the question is if AMI
uh,
2.0 systems can handle multiple tariff. Am I right, Shweta?
yes, yes, yes.
Yes, modern meters and hidden systems can support complex time of use, seasonal and customer specific tariff profiles. So, yes, it can, of course, handle multiple tariffs.
Um, audience also has a question on what shifts in data handling strategy are needed when moving to AMI 2.0.
The main change or shift required would be to make from periodic polling to event driven with high frequency data streams requiring better validation and storage. So that would be the main shift that is required. We'll have to move from periodic polling to event driven.
Right. What about considerations that are required when deploying AMI 2.0 in areas with frequent power outages?
In areas with frequent power outages, the meters must have reliable local storage and support for immediate event push before losing power so that we can be aware that a power outage has happened and necessary actions can be taken.
Yeah, Aparna, not sure if you got that.
Yes, Shweta, can you hear me?
Yes, yes. Okay, we'll go to the last question before we end the session.
Sure.
And we have many more, but we will compile and we will reply to you over email.
Could you
How
please
does
repeat the
AMI 2.0 ensure consistency of data when meters? Yeah, how does AMI 2.0 ensure consistency of data when meters switch between online and offline states
Okay, okay.
frequently?
Okay, okay. So the data is basically buffered in the meter and it is synchronized automatically once the connection is re-established to ensure consistency of data.
Okay. Thanks a lot, Aparna. I think we're just running out of time, so we will compile these questions and will reply to your email. Here is the contact details of our team. Thanks everyone for joining today and for your valuable time. Thank you, Aparna.
Thank you so much.